the common understanding is we need to succeed in this research, no matter how little budget investors are willing to spend on this, because it's important for humanity. And exactly that was my motivation to dig deeper into it.
The Rational View is a weekly series hosted by me, Dr. Alan Scott, providing a rational, evidence-based perspective on important societal issues.
Produced by Soapbox Media.
Hello and welcome to another episode of The Rational View. I'm your host, Dr. Al Scott. In this episode, I'm continuing my investigation into cold fusion, looking into potential scientific explanations of the excess heat and fusion products hinted at by Dr. Edmund Storms in my last podcast. There seems to be a dedicated research group that is working on these theories, and I'm eager to find out whether or not their hypothesis, called condensed plasmoids, can stand up to skepticism. If you enjoy what you're hearing, please press like on your podcast app, share it with your friends, join our discussion group on Facebook, The Rational View. Lutz Jaitner from Hamburg, Germany, is the father of 3 adult daughters. He holds a Master of Science degree in physics from the University of Hamburg. Lutz started his career as a designer and developer of multiprocessor hardware, after which he worked as a consulting engineer. Lutz is the programmer and operator of a public cloud service for neighborly help groups, Obelio eLETS service. Around 2006, Lutz started to evaluate the available literature about low-energy nuclear reactions research. By 2015, he found an explanation how the reaction might be facilitated by an ultra-dense plasmoid state of matter. It took him until 2019 to work out a quantum mechanical model of this state, to program a simulation tool for it, perform the simulation runs, and document this theory on his website. Lutz, welcome to The Rational View.
Hi, Al. Thanks for reaching out to me.
So, why did you get involved in low-energy nuclear reactions research back in 2006? What prompted you to enter this field?
Actually, I was doing some political research and found out that there is a source of energy which is kind of suppressed by established forces in the energy market and beyond. And once I understood that this initial finding of Fleischmann and Pons back in 1998 was not a fraud, but in reality was an opportunity for humanity, I got very interested and I tried to research the primary literature that exists. After so many years of research, there were thousands of scientific papers on the subject. And the first thing that I did was finding out, is that real? Is it something that I can believe with my physical understanding? And after some weeks, it turned out to be very real. There was not a single indication of fraud. However, I noticed that the people working in this field had no funding, so they were private people or pensioned professors, or with the exception of the military, interestingly. So the Navy in the US was researching that, and a group at Stanford University is also engaged in it. And that indicated to me that this is a political topic. It's not only about research, it's also about a political battle in the energy market, not to promote this new field too early before certain sources know how to monopolize it. This is my taking on it. This is not something that is said publicly, but the impression I got from looking through the literature.
So what particular research convinced you that this was not pseudoscience, that this was actual real results? What convinced you?
Let's compare that with magnet motors, which is certainly pseudoscience, right? There is a free energy movement around in the world, and people are building magnet motors and showing videos how they produce energy out of nothing. And if you compare that to cold fusion or LNER, you notice that in the magnet motor field, there is almost no scientific reasoning where the energy comes from. There is no good documentation in form of scientific papers, what they have done, under which conditions they saw the effect, how large it was, and so on and so on. There is a complete lack of data and an overabundance of claims. And if you compare that with the cold fusion research, you see the exact opposite. You see experienced scientists doing very, very careful measurements in calorimetry, which takes months, if not years, to perform. And then there is a lively debate whether they did everything right and the measurement is really precise enough to make the claims that the papers do. And there is a yearly conference called ICCF, which is a meeting, let's say, of worldwide activists in this field. And I participated in these meetings, and it is so obvious when you talk to these people that they are serious. They are not looking after investors of defrauding somebody. They do it for humanity, basically. This is the common understanding is we need to succeed in this research, no matter how little budget investors are willing to spend on this, because it's important for humanity. And exactly that was my motivation to dig deeper into it. And of course, it was not clear what exactly is the source of the energy. The finding was clear. There is heat coming out under certain conditions, and these conditions are weird. Very, very very different experiments were taken, and the same effect was seen. So that made me, from a scientific standpoint, very curious. I wanted to understand, how does it work?
Right. You came up with a hypothesis called condensed plasmoids as a potential scientific explanation of what's happening in low energy nuclear reactions. Could you provide us with how you came to that conclusion and give us a brief overview of what it means?
Yes, sure. So when I studied the literature of cold fusion research for several years, I came up with certain convictions. I was convinced that hydrogen is not fusing with hydrogen in any of the experiments. This was an opposite to most researchers' opinion. So I disagreed with the basic assumption that deuterium is fusing with deuterium in the lattice of palladium. I thought this is outright wrong, and the indication for that is if you look at the ash that comes out of a experiment, you are not only seeing helium, which was measured a number of times, but you see a zoo of almost all elements in the periodic table. Now, this finding of so many different isotopes coming out of the reaction is completely at odds with the assumption that deuterium is fusing with deuterium. So I was sure about that one. The next thing was I need enough energy to produce heavy elements or certain outcomes of the reaction, so the fusion energy of just a single atom of hydrogen with any other sort of atom is not large enough to explain that, for example, nickel and light hydrogen produces silicon or calcium or magnesium or aluminium. This, from an energetic standpoint, that is not enough to do. So something else needs to go on than a simple fusion between one hydrogen and one other element. So I tried to figure out from a quantum mechanical standpoint what can provide a multi-fusion or any other mechanism that gives enough energy to do fusion and fission and produce all the many elements. So that was the initial reason why I was using quantum mechanics. I thought that in a direct way, nobody is able to understand why fusion happens at all. The Coulomb barrier is too large to allow fusion, and normal matter doesn't fuse. Why does it fuse in these experimental setups? That was completely unclear, and I was completely disagreeing with Fleischmann and Pons with their theoretical assumptions.
The Coulomb barrier, just for the people who aren't nuclear physicists, the Coulomb barrier is the repulsion, the electrostatic repulsion between nuclei, because the nuclei are both positively charged, they repel each other. So there's this barrier that you can't push them close enough together to get the nuclear force to create fusion. And this is why in hot fusion, people accelerate particles together at high speeds, is to get past that Coulombic barrier and allow the nuclei to interact and create larger elements. So this is the main difficulty with cold fusion, is that cold fusion doesn't typically have the energies necessary to get over this barrier. Is that a correct statement?
This is precisely right what you said. This was a good explanation of the main obstacle in the theoretical understanding of cold fusion or LENR. So because of this, I thought that I need an intermediate state. So in a direct manner, fusion is impossible. But maybe there is a new type of physical object that first creates out of the experimental conditions. And this object then has the properties to allow for fusion. So this was a new way of approaching LENR. Nobody else did this before. So the assumption of an intermediate state was elemental. It was fundamental for my work. And the closest that I have found in the literature is the saying of the nuclear active environment. Have you heard about this term?
Not really, no.
I think Edmund Storms coined this term, the nuclear active environment. So this was the closest thing I found, and there was no explanation what exactly this nuclear active environment is. So when I talk about the intermediate state, I mean nuclear active environment, the thing that allows for fusion. Now, how do you come to an understanding of this thing? I used a quantum chemistry program, off-the-shelf program, and tried to arrange atoms in different ways. So my first attempt was putting hydrogen, 4 hydrogen atoms in close proximity to a nickel atom. And I wanted to know, what does it do quantum mechanically if I do so? If I reduce the distance further and further, what comes out? Will it create some new sort of state or not? Is it ordinary matter that comes out, or is it something special that I see there? And the answer was nothing special comes out. It was a complete failure. But with this experimenting, I made an interesting discovery. If I put a row of nickel atoms in a line, and then make this the distances between the nickel atoms smaller and smaller and smaller, something very interesting happens. The electrons are no longer localized to one of the nuclei. They can move freely from one nucleus to the next. And because of this new freedom of movement, the electronic states are lowered. So the electrons fall into a lower orbital, so to speak, if you do so. However, it takes energy to create this object. So it was still not a new type of matter, but it was interesting enough that it triggered my theory. So I thought, okay, what would be necessary to make this thing more stable and to create it in nature? I cannot grab atoms and put them together. I need some trick to do so. And I thought maybe a current does it. If I have a plasma and a very strong current is flowing, this creates a Z-pinch. A Z-pinch is a plasma column or wire of plasma, so to speak, which is compressed by magnetic forces if the current is very strong. And I thought, hey, this is a good way to compress matter. Let's find out whether I can make an intermediate state with it that explains LENR. And I very soon found out that the software that I was using is way too slow. I would say at least 10 orders of magnitude too slow to compute what I had in mind. So I was, first of all, programming my own software. I was creating a model of these condensed plasmoids, which is, as I said, a Z-pinch, a very small, very thin column of plasma. And because of the cylindrical geometry of this object, I could make computation much faster. So I was abstracting from individual atoms. I was assuming a very dense column of positive charge in the middle of this cylinder and using that as the potential with where the electrons are moving in.
Before you go on, the Z-pinch phenomenon is a real phenomenon. This is something that they use in hot fusion in tokamaks to control their plasma. Is that correct? They use the idea of the Z-pinch to keep that hot plasma dense.
Yeah, and this is a good point in time to explain the difference between cold fusion and hot fusion. So the Z-pinch experiments in hot fusion try to use very large currents like mega amps to pressurize the plasma, and at the same time they want to have this plasma very hot, as you said, to allow for fast enough collisions between the atoms so that they fuse. Now with mega amps of current, you're automatically getting a very hot plasma because there are losses and the current is heating up the plasma. And if you make the current small enough, like having only 10,000 amps, the plasma will radiate away its heat very rapidly. In less than a microsecond, it cools down to ordinary temperatures. And the good thing about this cooling down is that there is no thermal pressure inside the plasmoid. So with hot fusion, you have difficulties to pressurize, to make the plasma very dense because it is hot and heat creates a pressure. And in cold fusion, the opposite is true. The object cools down so fast that you almost have no thermal pressure. And the whole thing is compressed further and further from the magnetic field. Interestingly, the thinner the object gets, the higher the magnetic field becomes, and it collapses entirely to the quantum mechanical limit. So there is a certain minimum current you need to achieve that. And once you exceed that current, the object condenses into a range that is potentially smaller than the radius of an atom. So this plasma column, although it is very densely packed with nuclei, is thinner than an ordinary atom. And this explains why you have fusion, because the nuclei are so close to each other. They are also shielded by very dense electron gas. So the positive charge is kind of compensated from the electron gas. And the magnetic field gets in the order of 50 megatesla. To put that in a perspective, if I'm a researcher and build my own lab for some scientific measurement, I will have difficulties with coils to create a magnetic field larger than 10 or 20 Tesla. That is the experimental limit, what you can do in a lab. And we have 50 mega Tesla in these objects. This is astronomically strong magnetic field, and therefore the matter density is 100,000 times larger than in ordinary matter.
And does this magnetic field then explain why the electrons don't fly apart? Because they're obviously very densely packed. You're saying that as I read your paper, you're saying that the plasmoid is strongly negatively charged. So what is it, the magnetic field that keeps those electrons from flying off?
Absolutely. So a slow electron would just fly away from the object. That happens. You can measure that the object is emitting electrons with a energy of 2 to 10 kilo electron volts. This speaks a language about the negative potential in the core. So once an electron slows down, for example, by means of scattering against the nuclei, it will be lost. It will fly away. But if it is fast enough, if it is, let's say, at least 10% of the speed of light, it will stick to the core, because the magnetic field is bending the path of the electron towards the axis of that object again and again, so it cannot escape. This explains the pressure. This is the mechanism how it builds up the pressure.
So you've put together a research group, I think, to work on this. I saw you had a website on condensed plasmoids with several people. Looking at the people in your group, none of them have a PhD in physics. For many people, this might add a level of concern about the viability of your work. Has your hypothesis been published in a peer-reviewed journal, or has it been reviewed in any way by scientific experts in these fields?
Yes, it is published in the main paper, or what is this called, magazine? Journal of Condensed Matter Nuclear Science.
Okay. So it's been peer-reviewed?
Yes, peer-reviewed. It is a shortened version of my long paper. The original paper was 100-page long, and the reviewed version was something like between 20 and 30 pages. So I had to leave out many details how I came to this solution. Nonetheless, there was a lot of scrutiny before I was allowed to publish this. I also presented that theory at ICCF and got surprisingly positive feedback from many researchers. I didn't expect that, because I am disagreeing with most of the researchers there from a theoretical standpoint, and I was expecting mainly resistance, and that was not the case. So people understood that the thoughts that I'm putting in make sense.
So this is a very, I would say, new idea. There's a lot of, like, you're basically positing a new state of matter that no one's seen before here. How much new physics is involved in this model? At one point, you mentioned that EM, electromagnetic interactions between electron current and excited nuclei, result in de-excitation of the energetic nuclei before they can emit gamma rays. Has this been observed anywhere else?
So let me first make a distinction. My paper speaks of the main theory, which is a quantum mechanical description of this intermediate state, which I call condensed plasmoid. And then there are certain hypotheses which I'm putting on top of this theory. And they are of a different subject. For example, they want to explain the outcome, what isotopes are created, or the outcome, why is no gamma radiation or no neutron radiation seen, and all this. This type of or this part of my paper is not well funded. It is just the aftermath or the outcome of when you try to use the theory, what can you do with it? And there are certain arguments behind these hypotheses, but to compute that in a physically precise manner would be a paper in itself. It would take a lot of effort to make, for example, to compute the tunneling rate. It would be very important to compute that. Also, if you are referring to the cooling mechanism that I put in there, that requires a solid computation. I did only a hand computation, a very simple-minded computation that shows me that this is plausible, but it's not proven by this calculation. It is a hypothesis, right? And it explains why there is no gamma radiation coming out and why all the isotopes that are created, or most of them, are stable instead of radioactive.
Hmm. So has there been any rebuttal published in the literature? Have you experienced pushback from the scientific establishment on your theory?
After the years after my presentation at ICCF, I saw a decline in interest. So the interest level was good at the beginning. I stayed in contact with a number of researchers who then also tried to do some experiments along the line that we do. But that is a small group of people. I haven't created a revolution, and I did not even try to. My reasoning was, it's good to put it out into the public. If somebody else finds out something similar, he will most certainly search in the literature what is already known, will certainly contact me, and then we have a scientific dialogue and we can move forward. So far, this has not happened. So our group is alone, so to speak, almost alone in the application of that theory into a practical apparatus for energy creation. And I must say that our attempts to do so are to a certain degree successful. We were able to prove a number of predictions that came out of the theory. For example, we see a very strong difference between an ordinary glow discharge and a connection between the electrodes with a condensed plasmoid. That is sharply different. An ordinary glow discharge would draw a current of some milliamps in our apparatus, and we see thousands of amps going through the plasma discharge. And that makes us comfortable that there is something we can measure. And it even looks like it is creating energy. So it lives for a certain time span. And during that time span, it is creating energy. And the energy comes out in terms of fast electrons. So this is kind of a proof point towards the assumption that the nuclei are cooled by electrons, because now the electrons are getting faster by the cooling process, and we see fast electrons coming out. And that is very useful. Fast electrons are useful for many things. You can create heat with it and whatever.
So what magic do you need to do to make a condensed plasmoid of your type? That, like, what are there special initial conditions that need to be set? Like, why does, for example, palladium electrolysis create this? What distinguishes this from any other arc discharge?
Yeah, palladium is special. I will explain that at the end. To create a condensed plasmoid is extremely simple. So it's astonishingly simple. An ordinary spark is always creating a condensed plasmoid without any exemption. So when you see a high-speed video from ordinary lightning, you see a precursor running through the sky, or many of them, which are comparably slow in motion, so they can be filmed, and they look like a little ball lightning flying through the air with a glowing tail after it. And this object leaves a conductive path in the air. And once this object that flies through the air hits the other pole, let's say the Earth, then this conductive path all over a sudden draws current in the order of 100,000 amps or more, maybe even million amps. So the interesting thing is, before that happens, the interesting thing is the leader. Why is there a conductive path so stably established for such a long time in the air? If that would be normal ionization, it would have decayed way before the actual lightning occurs. So this type of object that you can see with these leaders are condensed plasmoids. They can get at as long as 200 kilometers, and even longer condensed plasmoids can be seen in the corona of the sun. So you see this filamentary plasma if you look at the sun's atmosphere, and they exist in very thin gas. This is in outer space, so to speak. This is not close to the surface of the sun. So what is the reason that there are plasma filaments, and why is this plasma as hot as 50 to 100 million degrees Celsius, whereas the solar surface below is only 6,000 Kelvin? Something creates a lot of energy in outer space in very thin gas. It seems to align itself along magnetic field lines. And all these properties fit nicely into my theory. Because if you assume that these condensed plasmoids are winding up like little coils, which is a sort of an instability, they how can I say that? A plasma column with a large current in it tends to form a helical structure instead of just a linear thing. And if you have this helical structure, then it will align to the external magnetic field lines that exist somewhere and will increase that field by orders of magnitude through its own current. And this is what happens at the sun, and this is what producing large amounts of energy there, and maybe even within the sun. Nobody knows that because you can't look inside of it. But my reasoning is that maybe the assumptions of the hot fusion guys are completely wrong. Maybe even the sun uses cold fusion to do what we do. So these objects have been over the course of more than 100 years. There are many experiments in history which were indicative for condensed plasmoids long before Fleischmann and Pons.
So I think, we're taught that any sort of spark discharge is just a column of electrons going from your cathode to your anode. And you're proposing that these are actually condensed plasmoids in all cases?
Yes. I'm not the only one saying this. So the real discoverer of condensed plasmoids is Kenneth Shoulders, or let's say together with Winston Bostick. So he tried to experiment with very small currents and large voltages, and he found out that he is able to create new types of objects that is able to ionize away matter in a way that cannot be explained by the energy amount that he puts in. So he saw these ring-shaped and helical structures that my theory describes decades before I did, and he did thorough measurements on it. So he was able to determine the kinetic energy of electrons coming out of these objects. He was able to determine that these objects contain negative charge en masse, which exactly is what my theory says. So
what other predictions does your theory make, and what are you hoping to validate in the lab?
So we are currently doing electrical measurements directly on condensed plasmoids. And we are very lucky that they stay connected with the electrodes for long enough to do so. And an important parameter is the impedance of such object. So we see, for example, if the pressure is very low, the impedance gets very low, let's say less than half an ohm on a distance of 4 centimeters, which is absolutely not normal for a glow discharge or for an arc or whatever object that people know. And when the pressure is higher, the resistance gets higher, but also the energy production gets higher. So we see interesting phenomena. So this is the first thing. And of course, we want to achieve a situation, or we want to measure conditions where the energy amount is larger than the energy we put in. This is our first goal. When we have that, we can try to build an apparatus that makes use of that energy. Other experiments you could do is, and partially we did that already, you could find out what happens if a CP dies, a condensed plasmoid. If it dies, what happens then? You should see a kind of a micro explosion, a sharp click, because at that point the current stops flowing that previously was flowing in these plasmoids, and that is creating some noise, electromagnetic frequencies in the outer environment. And we see this very clearly in our experiments. So the death moment of a CP is such a significant thing, it is very easy to measure. And it's kind of a signature. When you have these objects, there is a click at a point in time where your electrodes are completely calm. They cannot create this click. It must come out of these objects.
That's very interesting.
And it coincides with the moment when the current goes to zero. So it is not an arbitrary point in time. It exists at the right moment in time, what the theory would tell you. And then you can watch the traces that these objects do on surfaces. So when these objects hit surfaces, they leave engravings there, which are very special. They are described in my paper in many forms and shapes, and we see them in the microscope. We can create these objects with 100% repeatability, and we see all the engravings that have been observed in other LENR experiments. And this brings me back to your special question about palladium and electrolysis and things like that. So I believe there is a misunderstanding in the community. I believe that if you have electrolysis and you do it with a high current density, you're getting microsparking. So around the cathode, there is a depletion layer. The positive ions move towards the cathode and get discharged, so neutralized. The negative ions move away from the cathode. And then in this small sheath of liquid, there is mostly only water left, because all the ions are moving out of the zone. So it's kind of the cathode is insulating itself electrically. And this sheath, this non-conductive sheath, is extremely thin, extraordinary thin. And all your voltage drop that you see, or most of your voltage drop that you see in your electrolysis, falls across this insulating sheath, this depletion sheath. And if you drive your current high enough, there will be discharges through this sheet. It's like a little spark occurring, like a short circuit that discharges the electrolyte against the cathode. And that creates plasma. And the plasma, by chance, creates condensed plasmoids. And also by chance, they have a certain lifetime. And if you're very lucky, then the same condensed plasmoid receives a discharge again and again and again, and each time it grows a little bit. And this growing leads to a cratering of the cathode, and that has been clearly seen in all the experiments where excess heat comes out. You see characteristic craters in your cathode. And my model is that in the middle of this crater, there is a condensed plasmoid, and that gets energy again and again of microsparking. And this is the mechanism how you create cold fusion, not in the palladium, not in the water, but in these condensed plasmoids that are attached to the cathode. So the point where the heat comes is these little craters. Nowhere else you see heat coming out. It's only in these craters. And I have seen infrared videos from a cathode, which clearly shows that. This is little flashes at distinct points on the surface of the cathode where the energy is created. It's not a homogeneous effect. And when you look at the nuclear products that come out, they will not be found in the metal of the cathode. So it's not in the metal where the reaction occurs, because there is an absence of reaction products. All the products you will see in the outcoming gas and in the electrolyte. which once again speaks a language in terms of where the reaction occurs.
So palladium is better for this?
Well, there is something very special about palladium, and I need to explain that. When you measure the mobility of hydrogen atoms in the palladium lattice, you find out that light hydrogen has a much lower mobility than deuterium. So it is like a two-fluid plasma in a solid state. So the plasma consists of the electron gas that exists in the metal always. So a normal metal is a one-fluid plasma. And here you have a two-fluid plasma. You have highly mobile deuterons as the positive charges of a plasma, and you have electrons as a negative gas. And my suspicion is that this two-fluid plasma can, if you send a strong current through it, can create condensed plasmoids even at the surface, even without this microsparking. That is seen, for example, in thin film experiments with palladium in deuterium atmosphere. You see that at certain points in the film, in the palladium film, you see explosions and destructions of that film. And they occur if you send a current through this very thin film. And it leads to a condensed plasmoid because you first had a plasma, a two-fluid plasma. You're sending a current through, so you have a plasmoid. And apparently that can condense. And this is very specific to palladium. It only happens in palladium. No other material is known to produce this kind of effect in thin films. In all other experiments, you need to have a plasma, for example, with cavitation or with glow discharge or with sparking or with whatever it is. You need to have a plasma before you see excess heat. Best example for that is plasma electrolysis. That is much easier to do and to create large amounts of excess heat. Mitsuno did this. He had tungsten electrodes and did plasma electrolysis in water. And he saw excess heats in the order of 100 watts in a little bottle. Very easy to do. And there you can imagine that the plasma is instrumental in creating that heat. Because when he reduces the current density such that the plasma stops up and the electrolysis still occurs, no excess heat comes out.
So what does this mean if your hypothesis is correct for the field of LENR? Does this explain the difficulties people have had with reproducing it in the past? Does your hypothesis?
Absolutely.
Can you maybe expand on that a little bit?
Yeah, sure. So to create a condensed plasmoids, you need a few hundred amps only. Now, these objects have not the highest possible density, and the fusion rate is very low. However, these objects have a long lifetime. At these amounts of current, the lifetime is increased by partial ionization. So not all the electrons are delocalized, but only the outer shells are delocalized. And these kind of objects are almost stable. They can live for hours if you want. So it's very easy to study these objects, very reproducible once you engage in this kind of research and you know what you do. It's no longer black magic. You can do this in 100% of the time, you always create these objects. Now, if you make your current stronger, you will see excess heat coming out, again, with 100% reproducibility. And then you're left with the practical difficulties you need in electronics that gives you the pulses of that strength. You need to have a mechanism that harvests the energy that comes out and makes use of it in some sort of way. So the whole thing would stop to be a black magic if my theory would be applied to all LENR research, not just in our group. It would be a big improvement of the field, but it will take time before the community finds out that in each and every experiment, plasma is involved. This is not common sense. This is not what people believe to happen. I give you a very interesting example. People build multi-layer structures of palladium and calcium oxide, and then later on let deuterium diffuse through this multi-layer structure, and they see little amounts of excess heat coming out and certain transmutations occurring in these films. So it's absolutely non-obvious because this is just gas diffusion. How is this involving a plasma? How on earth is a plasma occurring? My belief is when these multi-layer structures are created, they certainly have plasma. They put the palladium sheet metal inside a plasma discharge vessel, and then they have a sputter target of calcium oxide, and they deposit calcium oxide by means of a plasma, and then they remove that sputter target by another sheet of palladium and cover it with palladium. And again, they have a plasma. And by chance, they are creating condensed plasmoids, which are embedded in these multi-layer structures. And at certain points in their structure, they have long-living condensed plasmoids. And once they send deuterium through it, oh yeah, you're getting transmutations. So you can imagine these guys doing these experiments will be the last ones to understand that each and every LENR experiment involves plasma. Or another very famous example, which is kind of interesting, is Andrea Rossi with his nickel powder hydrogen experiments. You're certainly aware of him and his experiments, right?
Mm-hmm.
So
yes, I've heard of him.
Yeah. So he found out that if he has a pipe with nickel powder in it and some hydrogen flowing through this pipe or some substances containing hydrogen putting into this pipe, he can create excess heat, but only if he is heating it up from outside with a coil, with a heating coil. And interestingly, the reaction doesn't work if this coil is heated by DC current. It just doesn't work. And if he has instead chopped DC current, like you have switching it on and off with a regulator with a switch, then the reaction works. What does that tell you? It tells you that the inductive spikes that are created by turning a current on and off and a magnetic field on and off is enough to create little sparks between the nickel powder grains. And that is the triggering event that allows the reaction to occur. So this is another very famous example where plasma is involved, but you wouldn't assume so, right? This is counterintuitive. You don't see the plasma and you wonder why this works and why it only works with chopped DC and not with normal DC.
Mm-hmm. So you're proposing that these plasmoids can be long-lived for hours, for example. just living happily on their own, circulating current at huge amperes. They should be observable, shouldn't they? Shouldn't you see light from them? Could you not
Yes,
look for the emissions?
it has been observed. So I think the name is Bogdanovich, a Russian researcher, had a very simple experiment. He was having a small outlet for water. He was having a stream of water running down from one electrode to another electrode. He was putting high voltages between these electrodes, and he saw some glowing phenomenon occurring. And then he was switching off his high voltages, and astonishingly, there were objects living for hours after the experiment and still emitting light. So, yes, indeed, these objects can emit light. They not always emit light. They can have so small currents in there that no light is occurring. And by the way, irregular ball lightning is such an object. So a ball lightning is normally glowing very bright. And I have seen photographs of a group of researchers who were creating artificial ball lightnings. That is possible. You can do that. And interestingly, they saw that some of the ball lightnings lived long enough that the glowing stopped and they became kind of gray objects. They were, if you had a light background, you could see this ball in front of this light object, and it was the result of a previously light or bright ball lightning. So both is possible. Kenneth Shoulders was talking about a dark state and a white state of these kind of objects, and this is exactly what happens. And the difference between light and dark is just the amount of current that flows, simply.
Interesting. Well, this has been very informative to chat with you about your hypothesis. I really learned a lot about it. I appreciate you coming on to chat with us about condensed plasmoids, and I hope we can learn more about these as time progresses, and maybe this is going to come to the forefront of physics and save the world. Wouldn't that be nice?
Yeah, I would be delighted, but I'm also scared. Energy is a political thing, and there are enough forces who don't like cheap energy in a decentralized manner. So we are kind of afraid by means of what we are doing. And we keep doing it because we see the importance for humanity. And I think there is a real chance, a realistic chance, that we are able to build an apparatus that is useful to create energy.
Oh, looking forward to seeing that demonstration. So thank you for coming on The Rational View and chatting with me. I have a final question for you that I asked some of my guests. What science fiction interests you? Do you like reading science fiction books or movies?
I did read some science fictions in the past, but I am not a fan of it. And I try to. My life is so exciting. I don't need to read fiction of any sort. So
Yeah, excellent. So for coming on, I'm going to send you a Rational View T-shirt for your time. Thank you very much, Lutz.
you're very welcome. Thanks for reaching out. This is important that the message comes through, that more people are starting to look at it, because it is a political hurdle that holds back this type of science. There is still no mainstream institution taking care of the research, and this is very bad for the field. It would progress much faster if we come out of this smearing attempts that occur against our research. And the prerequisite for it is just spreading the word, and you're doing a good job in this. And I thank you for that.
Thank you, Lutz.
If you'd like to follow up with more in-depth discussions, please come find us on Facebook at The Rational View and join our discussion group. If you like what you're hearing, please consider visiting my Patreon page at patron.podbean.com/therationalview. Thanks for listening.